Hello friends, welcome to my lecture on correlation and regression. This is my first lecture on correlation and regression. Very often a relationship is found to exist between two or more variables. For example, blood pressure of a person and his age, rainfall and crop yield, consumption of food and weight gain, height and weight of a person, the pressure of a given mass of gas depending on its temperature and volume. For practical applications we often are interested in obtaining a linear relationship between the variables. Suppose x and y are two dependent variables, we wish to approximate by a linear relationship of the form gx equal to a plus bx, where the constants a and b are to be determined so that the error defined by s equal to expectation of y minus gx whole square, which is equal to expectation of y minus a minus bx whole square is minimum. That is, the error is minimum in the least square sense. So, we may write this equation 1 as s equal to e y square plus a square plus b square into E x square minus 2b E x y minus 2a E y plus 2ab E x. Now, a necessary condition for a function of two variables, say here they are a and b, okay, you can see we want to minimize s is a function of two parameters a and b. So, in order for s to be a minimum, we must have the partial derivative of s with respect to a equal to 0 and partial derivative of s with respect to v equal to 0. These two equations are known as normal equations. Thus, the normal equations are, if you differentiate s with respect to a partially, okay, then you get partial derivative of s with respect to a equal to 2a minus 2 e y plus 2b e x. Okay. So, we get partial derivative of s with respect to a as 2a minus 2 e y plus 2 v e x, and we put it equal to 0. Similarly, when we differentiate s partially with respect to v, we get 2b e x square minus 2 e x y plus 2a e x. Okay. So, we get 2b e x square minus 2 e x y plus 2a e x equal to 0. Now, this equation, okay, this equation gives us a minus e y plus b e x equal to 0, or I can say e y equal to, this equation gives you e y equal to a plus b times e x. Okay. And from this equation what we get? We get a e x plus b e x square equal to E x y. Okay. So, we have two equations, this one and this one, okay, which are given by number 2. Okay. So, there are two equations connecting the two unknown values a and b. We can they are linear equations in a and b. So, we can solve them for the values of a and b, and when we solve them we get b equal to E x y minus E x into E y upon E x square minus E x whole square. Now, E x y minus E x E y gives us the covariance of the random variables x and y. So, covariance of x y divided by E x square minus E x whole square is variance of x. So, b equal to covariance of x y divided by variance of x, and when we put the value of v in one of the two equations, say for example E y equal to a plus b e x, we get the value of a. Okay. The value of a comes out to be E y minus covariance of x y divided by variance of x into E x. Hence, the waist fitting linear curve in the least square sense is given by y equal to a plus b x, where a is E y minus covariance of x y divided by variance of x into E x plus b is covariance of x y divided by variance of x into x. We can rewrite this equation we can rewrite this equation as y minus Ey equal to covariance of xy over variance of x into x minus Ex. Okay. So, we have this equation, variance of y minus Ey equal to covariance xy over variance of x into x minus Ex. This equation is known as the regression line of y on x. Okay. For a given value of x, you can get the approximate value of y using this equation. So, it is called as the regression line of y on x. Similarly, the regression line of x on y, if you are given the value of y and you want to get an estimate of the value of x, then we need the regression line of x on y. So, in a similar manner we can find the regression line of x on y. It is given by x minus Ex equal to covariance of x by over variance of y into y minus Ey. Now, since the point Ex Ey, okay, satisfies both the equations 3 and 4. Okay. So, now, you can see if you put here the point Ex Ey in this equation, then you see Ey minus Ey equal to 0, Ex minus Ex equal to 0. So, 0 equal to 0. So, Ex Ey satisfies this equation. Similarly, here Ex Ey satisfies this equation, and therefore, it follows that the two regression lines intersect at the point Ex Ey. Ex Ey be also denoted by mu x mu y. So, they meet at the point mu x mu y. Okay. Now, if Ex square and Ey square exist, okay, then the regression coefficients of y on x is denoted by beta by x and is defined as beta by x equal to covariance of xy divided by variance of x, and the regression coefficient of x on y is defined as beta xy denoted by beta xy and is defined as beta xy equal to covariance of xy divided by variance of y. Now, using these regression coefficients, the regression line of y on x, okay, the regression line of y on x which is y minus mu y equal to covariance of xy over variance of x into x minus Ex, I can write it as y minus mu y equal to covariance of xy divided by variance of x into x minus mu x. I can write it as beta the covariance of xy over variance of x is the regression coefficient of y on x. So, beta by x, x minus mu x, and this equation which is the regression line of x on y can be written as x minus mu x equal to beta x by into y minus mu y. Okay. So, using the notations for regression coefficient of y on x and x on y, we can write the regression lines of y on x and x on y in this manner. Okay. So, this is your regression line of y on x, okay, and the other one is the regression line of x on y, this one, the regression line of x on y. Now, correlation coefficient, the Pearson correlation coefficient is a measure of the linear correlation between the two variables x and y. It was developed by Karl Pearson. If Ex square and Ey square exist, then the correlation coefficient between x and y is denoted as rho, or we also write it as rho xy, and it is equal to covariance of xy divided by sigma x sigma y. Now, covariance of xy by definition is Ex by minus mu x mu y, and sigma x is square root variance of x, that is Ex square minus mu x square, and sigma y is square root of variance of y, which is square root of Ey square minus mu y square. Now, the regression line of y on x, okay, using the definition of rho, we can write the regression line of y on x in this form. You see, we had y minus mu y equal to covariance of xy divided by variance of x into x minus mu x, okay, and rho is equal to, rho is covariance of x y, rho is equal to covariance of x y divided by sigma x sigma y. So, covariance of x y is rho times sigma x sigma y. So, I can write it as rho times sigma x sigma y divided by variance of x is sigma x square. So, we have sigma x square and then x minus mu x, okay. This cancels with this and we get rho times sigma y over sigma x, x minus mu x. So, y minus mu y equal to rho sigma y over sigma x into x minus mu x. In a similar manner, we can express the regression line of x on y in terms of rho, okay. We have x minus mu x equal to covariance of x by divided by variance of y into y minus mu y, okay. So, when you put for covariance of x y, you put rho times sigma x sigma y and then divide by rho y square, what you get is rho into sigma x divided by sigma y. So, we get x minus mu x equal to rho into sigma x sigma divided by sigma y into y minus mu y, okay. Thus, we note that this is beta by x, okay. This is beta by x and by our definition this is beta x by. So, when you multiply beta by x and beta x y, what we get? Rho sigma y over sigma x, okay, into rho sigma x over sigma y, and this is equal to, this cancels with this cancels with this, you get rho square. So, beta by x into beta x by equal to rho square. The two random variables are x and y are called uncorrelated if the coefficient of correlation coefficient rho is equal to 0. If x and y are independent variables, okay, if x and y are independent variables, then we know that expected value of x into y is equal to expected value of x into expected value of y, okay. Hence, covariance of x y is expected value of x y minus expected value of x into expected value of y, okay. This we know. So, when x and y are independent random variables, then E x by equal to E x into E y gives us E x into E y minus E x into E y gives us covariance of x y equal to 0. That is, now covariance of x y is equal to 0 means rho is given by covariance of x y divided by sigma x sigma y, okay. So, when covariance of x y is 0, rho equal to 0. So, if x and y are two independent random variables, then x and y are uncorrelated, okay. So, if x and y are independent, then they are uncorrelated. But we shall see that the converse is not true, okay. The converse is not true, okay. So, let us show it by means of an example. Let us show that rho is equal to 0, okay, but x and y are dependent random variables, okay. So, let us take this example. Let us say that the random variable x is uniformly distributed over the interval minus 1 to 1, okay, and y is equal to x square. Then x and y are uncorrelated. Now, we know that if the x and y, if x is uniformly distributed over minus 1 to 1, then the density function of x is given by the density function of fxx equal to 1 over b minus a. Okay. If it is uniformly distributed over the interval a b, then fxx is 1 over b minus a. So, this is 1 over 1 plus 1, that is 1 over 2 when x lies in the interval minus 1 1 and 0 otherwise. Okay. Now, we need to find the value of rho and show that rho is equal to 0. Okay. So, we have found fxx. Now, we need to find expected value of x. So, expected value of x is integral over x into expected value of x is integral over minus infinity to infinity x into fxx dx. Now, it is half over the interval minus 1 to 1. So, this is integral over minus 1 to 1 x into 1 by 2 dx. Okay. So, this is half into x is an odd function of x. So, integral over minus 1 to 1 x dx will be equal to 0. So, expected value of x is equal to 0. Now, expected value of y is equal to expected value of x square. Okay. So, expected value of x square means integral over minus infinity to infinity x square fxx dx, which will be equal to integral over minus 1 to 1 x square into 1 by 2 dx, which is equal to 1 by 2 into x square is an even function of x. So, 2 times 0 to 1 x square dx. So, what we get is x cube by 3, integral of x square is x cube by 3 over the interval 0 to 1, and this gives me value 1 by 3. So, we have got the value of expectation of x, expectation of y. Now, let us find the value of, because we want the value of rho. So, we need to find expected value of exy, expected value of xy. Okay. So, let me find expected value of xy. This is expected value of xy is y is equal to x square. So, we get expected value of x cube. So, integral over minus infinity to infinity x cube fxx dx. This is equal to integral over minus 1 to 1 x cube into half dx, and we get 1 by 2. X cube is an odd function of x. So, the value of the integral is 0 and we get exy equal to 0. Thus, covariance of xy equal to exy minus ex into ey equal to exy is 0. Okay. We have found ex equal to 0. Okay. So, this is 0 minus 0. Okay. So, 0, and hence rho equal to covariance of xy divided by sigma x sigma y. Okay, is equal to 0. So, coefficient of correlation is equal to 0, but we are given that y is equal to x square. So, coefficient of correlation is 0, but the random variables x and y are dependent. So, this is a problem which shows that the converse is not true. Now, let us prove the Cauchy-Schwarz inequality. We shall need this Cauchy-Schwarz inequality to show that the value of the coefficient of correlation, that is rho, lies between minus 1 and plus 1. So, if x and y are random variables of the same type, that means either both of them are discrete random variables or they are both continuous random variables. So, then expected value of x by whole square is less than or equal to expected value of x square into expected value of y square. Let us take psi to be a real valued function, okay, of the real number t. Okay. So, let psi be a real valued function of a real variable t defined by psi t equal to expectation of x plus t y whole square, where t belongs to r. Now, x plus t y whole square is greater than or equal to 0 for every value of t belonging to r. Therefore, it follows that psi t is also a non-negative function of t. Okay, psi t equal to expectation of x plus t y whole square is also greater than or equal to 0 for every value of t belonging to r. And therefore, we can write psi t as equal to expectation of x square plus 2 t x y plus t square by square. Okay, and this is equal to expectation of x square, 2 t is a scalar. So, plus 2 t times expectation of x y plus t square times expectation of y square, which is greater than or equal to 0. Now, let us denote expectation of y square by a, expectation of expectation of x by into 2 by b, and expectation of x square by c. Then psi t is equal to a t square plus b t plus c, which is greater than or equal to 0 for every value of t belonging to r. Okay. So, psi t is equal to a t square plus b t plus c, which is greater than or equal to 0 for every value of t belonging to r. Now, we have to see two graphs. Okay. This graph and this graph, they are both see a t square plus b t plus c, okay, is a parabola. Okay, it is a parabola. So, this is a parabolic curve. Okay, and from the graph of psi t, it follows that either, now since this psi t is always greater than or equal to 0, either psi has no real root, okay, in which case b square minus 4 a c, okay, will be less than 0 because it is a quadratic equation in t, or psi has a unique real root, in which case b square minus 4 a c equal to 0. In this graph you can see it has a unique real root. So, in that case b square minus 4 a c will be equal to 0, and therefore, combining this case and this case, okay, we have b square minus 4 a c less than or equal to 0. Okay. So, b is equal to 2 times e x y. So, b square is 4 times e x y whole square, and less than or equal to 4 times a, that is e y square into c, which is e x square. So, we get e x y whole square less than or equal to e y square into e x square, which proves the Cauchy-Schwarz inequality for the random variables x and y. Now, let us show that the correlation coefficient rho is bounded by 1, that is mod of rho is less than or equal to 1. So, by Cauchy-Schwarz inequality, for if you take any two random variables u and b, then expectation of u b whole square is less than or equal to expectation of u square into expectation of b square. Now, let us define u to be equal to x minus mu x and b equal to y minus mu y. Then from this equation, okay, we have expectation of x minus mu x into y minus mu y whole square less than or equal to expectation of x minus mu x whole square into expectation of y minus mu y whole square. Now, this is what you can see, this equation, this is nothing but covariance of x y. Okay. So, covariance of x y whole square, this is sigma x square, this is sigma y square, which is they are variances of x and y. So, we get covariance of x y whole square less than or equal to sigma x square into sigma y square, dividing by sigma x square sigma y square, we get covariance of x y whole square divided by sigma x square sigma y square less than or equal to 1, or rho square is less than or equal to 1, which implies that mod of rho is less than or equal to 1. So, this proves the result that the coefficient of correlation is bounded by 1. Now, let us take an example. The joint probability mass function of x and y is given in this table. Okay. These are the values of x and these are the values of y. Okay. If when x takes the value 0, y takes the value minus 1, okay, f x y, the joint probability mass function of x and y, that is f x y. This is the joint probability mass function. I am denoting the joint probability mass function of x and y by f x y. This is joint probability mass function of x and y. Okay. So, this is the probability that x takes the value 0, y takes the value minus 1. This is the probability that x takes the value 0, y takes the value 1, and this is the probability that x takes the value 1, y takes the value minus 1. This is the probability that x takes the value 1, y takes the value 1. So, if we the marginal density function, okay, f x x, this is marginal density function of x. So, f x x is equal to probability that x takes the value x. So, x takes the value 0, okay, probability that x takes the value 0 will be equal to 1 by 8 plus 3 by 8, okay, which is equal to 1 by 2, and then the probability that x takes the value 1, okay, is equal to 2 by 8 plus 2 by 8, which is equal to 1 by 2. So, f x x for x equal to 0, okay, this is the case when x is equal to 0, this is the case when x is equal to 1. So, f x x is equal to 1 by 2 when x takes the value 0 and 1 by 2 again when x is equal to 1. Now, let us find f y y. Okay. F y y is probability that y takes the value y. Okay. So, let us first find the probability that y takes the value minus 1. So, y takes the value minus 1. So, this will be equal to 1 by 8 plus 2 by 8, which is equal to 3 by 8, and probability that y takes the value 1, which is equal to 3 by 8 plus 2 by 8, which is this is equal to 5 by 8. Okay. So, the marginal density function of y equal to f by y, okay, is equal to 3 by 8 for y equal to minus 1, y equal to minus 1, and 2 by 5 by 8, 3 by 8 for y equal to minus 1, and for y equal to 1 it is 5 by 8. We have to find the correlation coefficient. So, we need to find the expected value of x and expected value of y. Okay. So, expectation of x, let us first find the expectation of x. It is the values of x multiplied by the corresponding probabilities. Okay. So, x takes the two values, okay, x takes the value 0, 0 multiplied by its the probability f x. Okay. So, x is equal to 0 multiplied by half, okay, plus 1 multiplied by 1 by 2. So, we get expectation of x equal to half. Expectation of y we can get similarly, okay, values of y multiplied by their corresponding probabilities. So, value of y is minus 1, okay, multiplied by 3 by 8, and then value of y is 1 multiplied by 5 by 8. So, 5 by 8 minus 3 by 8 is 2 by 8, which is equal to 1 by 4. So, expectation of x is 1 by 2, expectation of y is 1 by 4. Now, let us find expectation of x square. So, expectation of x square, x is taking value 0 and 1. Okay. So, 0 square means 0 multiplied by 1 by 2 plus expected value of we are getting the values of x as 0 and 1. So, 1 square, that is 1 multiplied by the corresponding probability, that is half. Okay. So, expected value of x square is half, expected value of y square we can find. Now, y is taking value minus 1 and plus 1. So, minus 1 square is 1, 1 into the probability is 3 by 8 plus 1 square means 1 multiplied by 5 by 8. So, we get it as 8 by 8, that is equal to 1. Okay. So, we have got the values of expectation of x square, expectation of y square. Now, let us find the expectation of x y. So, expectation of x y, okay. So, values of x are x and y take values x is equal to 0, y equal to minus 1, 0 minus 1, okay. Then 0 and 1, then x is equal to 1, y is equal to minus 1, so 1 minus 1, x is equal to 1, y equal to 1, so 1 1, okay. So, expected value of x y is multiply the values of x and y with the joint probability, that is joint probability mass function of x y. So, x is 0, so 0 into minus 1, okay, x into y multiplied by 1 by 8, okay. Then 0 into 1 multiplied by the joint probability 3 by 8, then 1 into minus 1 multiplied by 2 by 8, and then 1 into 1 multiplied by 2 by 8. Okay, so, how much is this? This is 0, this is 0, and here what we get minus 2 by 8, here we get 2 by 8. Okay. So, expectation of x y equal to 0, okay. And thus what we get, we have rho equal to covariance of x y divided by sigma x sigma y. Covariance of x y is expected value of x y minus E x E y divided by sigma x sigma y. Now, this is expected value of x y equal to 0. So, 0 minus expectation of x is half, expectation of y is 1 by 4, okay, divided by sigma x is equal to square root E x square minus E x whole square. Okay. Expectation of x square we found that is equal to half minus expectation of x is equal to 1 by 2. So, 1 by 2 square means 1 by 4. So, this is 1 by 4, square root of 1 by 4 is 1 by 2. So, we get 1 by 2 here. Okay. Now, let us find sigma y. Okay. So, sigma y equal to square root expectation of y square, it is equal to 1. Okay. Expectation of y is equal to 1 by 4. So, 1 by 4 whole square. So, this is equal to square root 15 by 4. Okay. So, we get here square root 15 by 4. Okay. This cancels with this cancels with this, and we get it as minus 1 by root 15. Okay. So, rho is equal to minus 1 by root 15, which is equal to minus 0.2582. Now, let us consider another problem. Let x y be a two-dimensional random variable uniformly distributed over the region R, bounded by y equal to 0, y equal to 0, x equal to 3, y equal to 4 by 3, x. Okay. So, this point of intersection is 3 4. Okay. Now, this is the region R. Okay. Region R is bounded by y equal to 0, x equal to 3, and y equal to 1 by 4 by 3 into x. Now, area of the region R is equal to 1 by 2 into base, because it is a triangle. So, base is equal to 3 into height is 4. So, we get 6. Okay. Now, since the random variable is since x y is two-dimensional random variable which is uniformly distributed over the region R. Okay. So, we have f x y equal to 1 by r means 1 by 6 when x y belong to r, okay, and 0 otherwise. Okay. We need to first find the marginal density functions. Okay. The marginal density function of x, let us find first. Okay. So, we have f x x equal to by varies from 0 to 4 x by 3 f x by into dy. Okay. This is the probability that x takes the value x. So, this is equal to by varies from 0 to 4 x by 3 1 by 6 dy. So, this is equal to, and here x when 0 is less than x less than 3, okay, we have f x x equal to this. So, this is equal to 1 by 6 4 x by 3, and this is equal to 2 x by 9. So, f x x equal to 2 x by 9 when 0 is less than x less than 3 and otherwise it is 0. So, we write it like this, f x x equal to 2 x by 9 when 0 is less than x less than 3 and 0 otherwise. Let us now find the marginal density function of y. F by y. So, f by y equal to, now this is the probability that y takes the value y. So, x varies, we have this region, okay. This is y equal to 4 x by 3, this is x equal to 3 and this is y equal to 0. So, x varies from 3y by 4 to 3. So, 3y by 4 to 3, okay, and f x y dx. So, this is 3y by 4 to 3 1 by 6 dx, okay. So, 1 by 6 times 3 minus 3y by 4, okay. So, this is 1 by 2 minus 1 by 8 by 1 by 2 minus 1 by 8 y, okay. So, f by y is given by 1 by 2 minus 1 by 8 by when 0 is less than y less than 4, okay. Y lies between 0 and 4, this is 3 4 point and 0 otherwise. Okay. Now, let us find expected value of x. So, expected value of x is x multiplied by its probability density function, and x varies from 0 to 3, okay. X varies from 0 to 3. So, 0 to 3 x times f x x, f x x is 2 x by 9 dx. So, this is 2 x square by 9, okay. So, 2 by 9 x integral of x square is x cube by 3. So, we put the limits and we get 2 by 9 into 3 cube, 3 cube means 27 divided by 3. So, we cancel this and get expected value of x as 2. Now, expected value of y. So, integral over by f by y dy, y varies from 0 to 4, and what we get is integral over 0 to 4 by times f by y is 1 by 2 minus 1 by 8 by dy. So, this is equal to 1 by 2 by square by 2 minus 1 by 8 by cube by 3. Let us put the limits and we get this is 4 square by 4. So, we get 1 by, so we get 4, okay, minus 1 by 8 y cube is 4 cube. So, 4 into 4 into 4 divided by 3, okay. So, this will be 4 minus 8 by 3. So, this is 3 4 12, 12 minus 8. So, 4 by 3. So, this is expected value of y. Now, expected value of x y. Okay. So, we take the joint probability mass function here. So, for now let us see, we have to integrate over this area, okay, for the joint probability mass function. So, y varies from 0 to 4x by 3, x varies from 0 to 3, and we have x into y, f x y dx dy, dy dx. F x y is equal to we are given f x y equal to 1 by 6. So, this is 1 by 6 times integral over 0 to 3 integral over 0 to 4 x by 3, and we have x into y dy dx. This f x y is equal to 1 by 6, okay, over region R. So, we have 1 by 6 integral over 0 to 3 x, and then we get y square by 2, and we have the limits 0 4 x by 3 dx. So, what we get is 1 by 6 0 to 3 x times y square means 16 x square by 9. So, 16 x square by 9 into 2, that is 18, okay. Y square by 2 means 16 x square by 9 into 2, 16 x square by 18. So, we get here 2 8 ja 16, and here we get 9, okay. This dx, okay. So, we have 8 by 6 into 9, 8 divided by 6 into 9, x cube, integral of x cube is x 4 by 4, 0 to 3. So, we get 8 by 6 into 9, and then we have here 3 to the power 4, that is 81 divided by 4, okay. So, 4 2 ja 8, okay, and 2 3 ja 6, and then we can cancel 3 9 ja 27, 27 will cancel, okay, 3 will cancel it as okay, 3 27 here, and 9 cancels 27 with 3. So, we get expected value of x y as 3. Okay. Now, we need to find expected value of x square, expected value of y square. Okay. So, expected value of x square is integral 0 to 3 x square into f x x dx, okay. And f x x we have found to be equal to 2 x by 9 over the interval 0 to 3. So, this is 0 to 3 x square into 2 x by 9 dx. It comes out to be 2 by 9, integral of x cube is x 4 by 4, 0 to 3 we get 2 by 9 into 81 by 4, okay. So, 9 9 is 81, and we get it 9 by 2. Similarly, we can find expected value of y square integral 0 to 4 y square f by y dy, and it comes out to be integral 0 to 4 f by y is 1 by 2 minus 1 by 8 y. So, 1 by 2 minus 1 by 8 y dy, and this is 1 by 2 by cube by 3 minus 1 by 8 by 4 by 4, and we get the value as 1 by 2 by to the 4 to the power 3. So, 64 by 3 minus 1 by 8, 4 to the power 4. So, 4 into 4 into 4 into 4 divided by 4. Okay. So, this cancels and we get this cancels with this, we get 2, this cancels with this, we get 2. Okay. So, this is 8 and here we get 32. So, 32 by 3 minus 8. Okay. So, we get 8 by 3. Okay. And so, rho x y equal to E x y, which is E x y minus E x into E y. This is covariance of x y. Okay. Sigma x, sigma y. Okay. So, we found E x y equal to 3. Okay. And E x equal to 2, E y equal to 4 by 3. Okay. So, 3 minus 2 into 4 by 3 divided by sigma x. Sigma x equal to square root E x square minus E x whole square. E x square we found is equal to 9 by 2 and E x we found to be equal to 2. So, 2 square is 4. So, we get this is 1 by 2. So, 1 by 2 square root and sigma y equal to square root E y square minus E y whole square. E y square we found to be 8 by 3. So, 8 by 3 minus E y we found to be equal to 4 by 3. So, 4 by 3 whole square. So, this is how much 8 by 3 minus 16 by 9. Okay. And this is LCM is 9, 24 minus 16. So, we get 8 by 9, that is 2 root 2 divided by 3. Okay. So, we get here 1 by root 2 into 2 root 2 divided by 3. Okay. So, how much is that? 3 3 are 9, 9 minus 8, 1 by 3. So, 1 by 3 divided by this cancels with this 2 by 3 and we get the value as half. Okay. So, rho x by equal to half. Okay. So, rho is equal to correlation coefficient is equal to half. So, this is how we solve this problem. With that I would like to end my lecture. Thank you very much for your attention.